Yes, thank you. So the idea, well, I'm not a machine learning, this is a machine learning seminar, and I'm not a machine learning researcher, but I'm interested in applications. I have lots of things to say about the applications. I will say some of those things here. The connection to machine learning might not be very direct or very clear. So my background, as said, is in old-fashioned symbolic AI. So I did my PhD on non-monotonic reasoning with Ilkka Niemelä back in the mid-1990s. And after that, I've been doing automated reasoning, decision-making, planning, diagnosis, and this kind of thing. So like symbolic applications, symbolic AI, and a little bit in the application side. And also some, lots of effort in doing applications while I was in Australia from 2006 until 2011. And I will say something about that too. So just to, what is the background here? What is AI? AI is trying to do things that require intelligence in some sense, and well, I'm interested in the not like AI inside a computer that talks or a robot that walks. I'm very much interested in AI in large systems. So a general statement about purpose AI could be like replicating and improving on human skills in managing complex either physical systems or complex virtual systems. So I'm now not talking about a robot or a talking computer program or like something like that. I'm really talking about like large-scale infrastructure, industrial systems, and that kind of things. Like society's infrastructure controlled and managed in an intelligent way. Of course, there's lots of other aspects in AI, like understanding what is human intelligence and so on, how to replicate that, but that might not be the only goal of AI. In my opinion, there is no clear border between AI and other IT and automation. So as soon as you start to be a little bit further from trying to replicate human skills exactly, it's very unclear what is the border of AI and something else. So this AI in those cases is simply like sophisticated, complex computation. So or is it still AI? It's unclear. Much of the most visible AI nowadays is things that people see in their everyday life all the time. Like you have a smartphone that understands speech or stuff that is needed for interacting. Computers interacting with human beings. And many of these things are very, very difficult simply because we don't really understand how the human brain works and how the human thinking goes. And the bottleneck in all these applications is the difficulty of actually exactly saying what are things people talk about and understand about. And that's the main reason, of course, why people want to use machine learning for these kind of applications. This is not the kind of things I'm really that interested in, or maybe my research does not apply to these kind of things really that well. And my interest has been then in industrial applications, which might be quite a bit different. Much of the things people would like to automate in industrial applications might not actually involve any humans at all. So for example, this human-computer communication aspect might be quite minimal there, or it might be very, very simple, simply because the computers, the AI doesn't need to communicate with the humans at all. And in that kind of applications, I will be talking about, for example, applications in electricity, power systems. Much of those things are about managing some complicated system, and the complexity comes from the complexity of the real world. But the key difference to the like AGI style AI is that building accurate models of those systems is typically quite feasible, and that's simply a product of the fact that these systems were built by human beings. Unlike human brain, these systems were built by humans, so it is generally possible to model them quite accurately. Of course, there are things that are not possible to model accurately also in these applications. And this is typically things that are outside the system. And typical thing in almost all industrial applications I could think of is some kind of aspects of demand prediction. I have a long list of industry areas in one of the next slides, and in all of these, is it about transportation, manufacturing, whatever, there's always a demand prediction problem in energy systems and so on. So human beings, large groups of human beings determine how much a certain service is to be used. And that is again like this HCI style AI problem. So how do you predict when is 100,000 people going to turn on their something heating system or something else? And for that kind of things, of course, one would need something like the type of AI, most likely based on machine learning, that could predict that kind of things accurately. But other than that, the system itself, energy system, transportation system, manufacturing, and so on and so forth, they can be modeled quite accurately. So the modeling there is not the kind of fundamental bottleneck as in the kind of AI applications where human communication is the core problem. And of course, in these kind of systems, replicating human skills might be completely unnecessary and uninteresting, and it actually might be a really bad idea, because if you're managing some really complex system, the human ability to do those same things might be actually very, very low. So you don't want to, in general, replicate human performance there at all. The biggest obstacles for progress is computational complexity. All kinds of planning, scheduling, and so on problems, they are NP hard, and if you add any kind of uncertainty or incomplete information and that kind of things, the complexity goes very quickly through the roof. So we are immediately talking about X-time hardness, doubly exponential complexity, and so on and so forth. So very, very high complexity. Those are the main obstacles in these kind of applications. Oops. So as a brief summary at this point, why is AI difficult? Two things. Difficult of modeling, you can't really say what something is. I mean, you can't really even define what is a chair, for example. That's a fundamental problem in AI, and shows up in lots of types of AI problems. And the other problem, which has been the core problem in the type of research I have been doing, is computational and conceptual complexity. Once you have the basic concepts and you know how to work with them, you have decision-making, planning, and whatever problems that are computationally so complex that you can't really solve them in practice if the system you're looking at is big enough, and usually they of course are. So here's my list of applications areas, and I would love that AI researchers would really think about all of these things, because these are full of problems, all kinds of problems, not just the kind of problems I was talking about the last slide, but also of course it's the HCI type of problems as well. I've been working on the first one, and I would be interested in working also on all of the other ones. And the basic thing, of course, is that in all of these industries, software is an important thing. So even if you did not have AI in these things, you still have software doing something. So that's one of the core commonalities between all of these. So what I believe that all of these will be fundamentally changed by having AI in them, completely different kind of software systems than what currently exists. And the change really comes through, first, at the first stage, implementing what those industries are doing by very high level of automation. Currently, all of these things require, small amounts of larger amounts of people. Some of them are automated much further than some others. For example, in the energy sector, most people who are working there are either people sitting in control rooms or people who are deployed once something actually goes wrong. But still, even those jobs can be assisted very much by different kinds of AI, and in some cases, the human beings can be replaced. In other almost everything else here very strongly relies on human beings for running these things. But yeah, what I'm saying here is that automation in all of these areas will go much further than where is it currently. And so first step is actually taking the automation level much higher, and the second step is actually transforming how these work to make them optimal in different respects, that in ways that are currently not possible or even imaginable. What I don't believe is that AI would have a strong impact by replacing human beings one by one. So that's why I'm not a huge believer in applications of the kind of AI that try to imitate human beings, because this is something that is very difficult, and you might actually not have to even do that kind of thing. And anyway, if you just automate individual human beings without automating a whole system, you are actually going to just preserve the current existing mode of operation of that company or organization. So I don't think AI as a plug-in in existing software system is going to really cut it. It can be very useful in specific applications, but that's not the AI revolution we should be talking about. And I think the fundamental thing that has motivated my current research is this. So if you're looking at current software systems run in any of those 10 or 15 industries are listed there, they are all managed by completely conventional software systems. And then embedding AI in this is very difficult for a number of reasons. So you would have to completely re-implement all of those software systems to actually make them intelligent in the way, how AI could make them intelligent. So typical things is that, well, there's data there, how do you access the data, what do you do with that data, what does the data mean, and so on and so forth. And if you want to control something, what are the control functionalities? There might not be any API that allows you to do all kinds of things. And this is especially true in cases where the processes there are mostly managed and run by human beings. So a very typical scenario is that there's some organizational or business process and it's not automated. The progression of that process depends on human users doing something, making the things work, and without human beings, absolutely nothing is happening there. And of course, that's not something where AI could be embedded very easily. And also, I think that the existing software industry is an obstacle for this. So what are they doing? They are producing software according to certain specifications. They don't care about AI or further automation than what their customers are currently asking. And software development processes are very slow and expensive. And it's what they are doing is something that certainly does not enable AI in any sensible way. Okay, I'm now through over my slides here in the right or most interesting order. I briefly explain our experiences, what we were doing in Australia in about 2009, 2011. So I was working at National ICT Australia in ICTA in Canberra, and starting in 2009, or until 2009, they were really happy us to do any kind of AI research we would like to do. So automated reasoning, planning, diagnosis, and whatever. And 2009, they were telling us, okay, now you guys have to apply your stuff to some real-world problems. And one of our group members had contacts to the electricity sector earlier. And so we thought, okay, this is a good idea. We can go and talk with all of the Australian electricity companies and offer our really great supervisory control, diagnosis, monitoring stuff that we could do really well and offer these things. So we have this great stuff. You want to automate your electricity networks to a higher degree for a number of reasons. Let's work together. And so we tried to do that. And it seemed very nice in the beginning, but then things started slowing down when it came to actually deploying the software with the electricity networks. And there were lots and lots of different kind of issues, starting from the fact that the electricity industry is very, very, very conservative. So it's run by electric engineers with little IT understanding. And electricity and power is a very, very tricky subject, because if you screw up with an electricity network, it can cost a lot of money, and there will be stuff exploding in transformers and power stations and whatever. So they were not really happy to have us actually deploy software. So what we actually did get to do is this diagnosis and monitoring part. So they were giving us a lot of data, and we could show that we can figure out from really, really long and complicated event logs what was the actual thing that went wrong there, and all kinds of things that helped interpreting the event logs to explain what is actually going on in the electricity network. But then when it came to the controlling the networks, there was just no. At this stage and a little bit earlier, we had already been contacting the companies that actually control the software that is used by practically all electricity distribution and transmission network companies. And these are these companies that sell both network equipment and the associated software systems. So the access to electricity networks, to actually deploying software, it always goes through to whatever companies the corresponding electricity companies are, whose hardware and software they are using. So we would have had to go to ABB. We actually did go to ABB. Or some of these others, and convince them that what we have is actually something that is worth deploying. And the story was always that, this looks really great. This is at a completely different level what we actually have, but you already have some company. I remember there was some Swedish company doing very, very primitive electricity networks diagnoses. And they will say, okay, this Swedish company already has this product that we are selling. And actually, our customers are quite happy with that, and they don't know about anything better, so there's no demand actually for anything more clever than this. So this thing died there. But it became very, very clear that to actually have a bigger impact there, you would have to either partner really, really tightly with some of these companies, or alternatively try to replace everything they are providing, which of course would have been impossible. So we did not really get very far with this. And okay, so it was a very, very nice experience, and I understood very, very well what would be facing us if we try to do the same thing in any other of these areas. And back to the drawing board, and try to think again what might be interesting and useful. We had a smaller project now, just 2 or 3 years ago, 3 years ago maybe, with Nokia. Also like industrial AI project, management of base stations for 5G networks. The problems here are a little bit similar to the ones in the electricity network case. So both are very, very highly automated. In electricity networks case, the demand for further automation comes from the fact that due to wind power, solar power, and potentially in the near future because of plug-in electric vehicles, the demand and production of electricity will vary a lot more than it has used to. So there's lots and lots of more stuff to do in the control room. The guys who are sitting in the control room and staring at the screen, trying to figure out whether something is going wrong, and sometimes adjust some network settings or closing some switches and so on. But that work is going to multiply when electricity networks are going to get more complicated. And the same story happens with 5G cellular networks. So they have control rooms, there's some guys there, but with current networks, the number of base stations is not really that high. So I can't remember what is the number in the Helsinki area. It's some dozens or something like that. But it's going to be 10 times or 20 times or 50 times more with 5G networks. So they can't do the same control stuff anymore with the same number of people. They would need dozens of times more people doing the same thing. So they need to automate. So that's what we were doing there. We were using reinforcement learning to to learn the best possible settings for 5G network base stations. The settings change day by day and hour by hour, depending on where the people using their mobile devices are actually located. So at some point they are at home and then they go to the whatever jobs, which is a different location. So there's lots and lots of things to control there. Nokia was also happy with the stuff we were doing, but they weren't really interested in deploying this one either. So it was clear that we would have to go through Nokia, and they would really have to get interested in our stuff. Maybe they will get interested in a couple of years, but the story would be the same. But one would have to go through these companies to actually do something interesting. So observations. Maybe I'm overgeneralizing a little bit, but still, this is the story I currently have based on my experiences in this and some other application projects. AI technology is very much in the periphery, and unless you really get to go into the core of the software systems that control some industrial systems, they are not really going to change the way those systems are operating. And this will dramatically limit the value potential of AI. There's certainly things that you could be doing by plugging in some piece of software to an existing system, and okay, it does something incredible that was not done before, but the bigger revolution is not going to happen that way. And my vision based on this was that actually large-scale application of AI requires doing software in a completely different way. So we can't rely on, have some great AI stuff being applied in some company or some organization. One could think of any Finnish public sector agencies, for example, by relying on their existing software systems and inserting some plugin there to have it actually do something really great and different. So what you have to do really is do software in a completely different way. So we need flexible, modifiable, and inexpensive software systems. So software should be much easier to make. And it should have the kind of flexibility that would enable integrating all kinds of AI stuff. And by AI stuff, I mean automated decision making, automated planning, automated diagnosis, automated everything in those systems. And all of these things require a deep understanding what that application is actually doing, and that doesn't currently exist. So if there's just data spread to multiple databases and nobody really knows exactly what that data means, that all of that is not going to happen, and you can't really control those systems anyway unless you have built in those functionalities there that allow you to control those systems. And I don't think that software should be written by human programmers anymore to actually enable all this happen. I will be explaining in the next slides what we are doing and what we want to do in a far larger scale. I was using here quite sort of dramatic terminology here, reimagining the software industry. I still think that much of the existing software technology can be kept as is and doesn't have to be reinvented, and actually replacing those things with something else, I don't really know what the point would be. I think most of the current software will be in use 10 years from now. there's no need to replace operating system programming languages, database management, and that kind of thing. So all of these things should be compatible what we want to do with AI in the next 10 or 20 years. The main difference, I think, are where does the software come from, how is it produced, how is it tested, and how is it deployed. And to enable the software to be more intelligent. At this point, I want to have a nice picture. I picked up one of my AI course pictures here, and the sort of general model. This is actually applies to lots and lots of different kind of scenarios. As you can see, this probably represents some kind of physical system. So it could be like a self-driving car, or some kind of industrial process, or some factory doing something. But I think this is a picture that applies to many different scenarios. And what I want to do first is actually do this part here. I have written long-term planning here, but it means just the top-level management of something. And as long as as long as this is not fully automated, there's lots and lots of human beings involved in this. There might not be much human beings involved or any human beings involved at the lower level things that are much shorter time scale and would require a very quick reaction, but at the longer term management of something, human beings are still a very central thing. And as long as humans are there, I think that the top box here is actually something that would often be called the information system. So how is some big system management? How are people making decisions about how this system is being managed? And then there are lower levels that require faster and faster decision making and reactions, and they are already in many cases very far automated. Here's a practical potentially near future application of the same architecture diagram. So assume that we have self-driving cars that can be sent from A to B. We don't have to care how those cars are implemented, but we might want to create a company that manages a fleet of 1,000 self-driving cars to provide taxi service in Helsinki, for example. And it would look like this. So there's the lower level things, lower level decisions, small time scale, and then there's the top level things, very long time scale, probably people deciding whether we need more cars and when do we have to get rid of those cars and so on and so forth. But then this could be instantiated, of course, in many other different ways. Anyway, my interest in this point is this one here. So how would complex software be created so that, well, currently I'm just interested in software that is used by humans, but that would enable the kind of automation required by all kinds of AI. And that's where we are going now. So we have a project since, Business Finland funding since 2018, and we have been doing this a little bit longer. And the goal is to produce software automatically and do that software at a high enough abstraction level so that you can do all the kind of stuff that AI enables you to do. So automated decision making and planning and that kind of things that could be embedded into software systems without actually any additional other programming. So at this stage, it's simply information. It's just conventional software, but done in a way that enables all the good stuff later. This is definition of, I don't know what is the official definition of information system, but information system web application software that involves typically some data storage thing, could be a data management system or some cloud service, and human beings doing stuff with the software. So looking at the data in the system, changing the data if they are allowed to do that in whatever way they are allowed to change it, and so on and so forth. And input is a very high level specification of the software's functionality. I will have some example on the next slides. And output produce fully automatically is an executable software system that can be deployed right away without any further work. So basic scenario is this. There is not really any AI in this yet, but I will be showing where we are going to go next. So we basically produce automatically this red box here. So everything between, let's say, data storage and external systems and the user interface facilities. So like a user UI could be accessed by a net browser or something else. So completely standard normal software. That's what we are currently doing. Here's an example of a way we are specifying software functionalities. One of the demo applications we currently have is academic journal peer reviewing and publication application. If I remember correctly, there's something like 6 or 7 or 8 rules. So we write, this is one of the most complicated rules in this application. We have 7 or 8 rules like this, and well, we have to of course describe what are these data types. A journal is an object with some components that you might imagine very easily, and our prototype software synthesis system produces the software application fully automatically from these 7 rules plus the whatever data definitions we have plus some access permission rules, and nothing else is needed. So we don't say anything about the user interface here, and that's one of the main non-trivial new things here. So we don't even have to do user interface programming. We can do it if we want to have a nice layout for the things on the screen, but it's not obligatory. And the interesting thing from the point of view of automated decision making and planning is that we could allow an AI to use these kind of rules to actually do with the software system fully automatically. So this is what this automated decision making thing would need. And it would not need anything else, and it would need exactly this. To decide whether to do something, yeah, you have these rules that explain what the AI could be doing. So here's this one rule explains how to create a new volume for an academic journal. There's 6 or 7 other rules. I can't remember. I'm not going to list them here, but like submitting an article, sending a review, choosing the reviewers, and so on and so forth. We also have permission rules that say when is somebody allowed to read or modify some data in the software system. Here's a simple rule that says that there's an article submitted to a journal. You can read these fields of that object if this condition is satisfied. So the current user is one of the reviewers, or it's the associated editor handling this submission, or if the user is the editor of that journal, for example. So these kind of very, very understandable abstract rules. No software code in the typical sense is needed for producing this and similar applications at all. So the applications are fully automatically produced from that kind of rules, and those rules are used in multiple ways for multiple purposes. And for example, given that rules that there's a certain functionality, things we are needed for actually producing the application is that we have to be able to test whether certain functionality is available for a certain user. For example, for displaying that functionality in a menu, what can you do? Can you do this? We have to decide that. Test the applicability of an action. This is one of the most complicated things here. So create software code for asking a user for inputs to use a certain functionality. So we produce that fully automatically based on this condition part here. Produce all the HTML, JavaScript, SQL queries and everything else to actually create a user interface that corresponds to this specific functionality. These two things, they might, I don't know whether they look simple or not. These are both computationally very hard. So NP hard and depending on what data types are involved, much harder than that. it's stuff that we have patented or is being patented currently. That's the sort of the core here, the user interfacing stuff. And then of course other types of code, execute an action, that's trivial. You just test the condition part is satisfied and then execute, well, do the changes in your database that are required. And then displaying data on the screen. Of course here you need to look at the permissions, whether somebody is actually allowed to see something and what fields of some objects should be visible for a given user. So these two first ones are very, very complicated, both conceptually and computationally. Well, we try to live in the real world of software, so many of those things in many cases can be reduced to ordinary SQL. The reduction is quite complicated, but we still use normal SQL databases in the bottom of this thing. Current demonstration applications, we have this university-related things. There's some social net, well, nice simple demos, blogging, website, copy of Facebook. There's the scientific journals, peer reviewing publication processes, and more applications are under development. So generally doing these things is quite easy. You just write these kind of rules. In some applications there's 3 rules, like blocking website, 3 rules, create a block, write a new block entry, and write comments to somebody else's block text. Very, very simple stuff actually. Software is produced in seconds. It's not very, very demanding. I said computation complex, one of the core problems there, but in practice the software is produced very, very quickly. So the next stage is embedding of more intelligence in the software systems. So based on rules like this, depending on the application area, you could be out automating the use of these rules. So of course in the current situation, these are user functionality. So human users can do this thing here, given that, well, with given inputs, as long as this condition satisfied, a human user can do that thing. But we could very trivially deploy all of these rules to be used by some automated decision making or automated planning program to do things automatically. So like goal-directed intelligent agents. There's a complex software system. User wants to do something, but he doesn't understand how the complex system works. This is typical in many types of information systems. So you would need to read some manual to explain how to do something, because what you want to do requires multiple steps. This automation to assist the user could be fully automated simply by specifying, okay, if your goal is this, I choose this goal, what do I have to do? I have to do this, and after that, that, and that, and that, and that. That could be completed fully automatically without anybody writing one line of code anywhere. Then, of course, I'm thinking of many other types of applications where this automation could allow the owner of the software to earn money. It could be like a financial sector, financial and banking, or something else. Write a decision-making agent that uses those actions, those functionalities to do something that has tangible value and monetary value, for example. And we could be embedded in many other types of things in this framework quite easily. Future thing, coupling with lower levels of complex intelligence systems. So what we are now doing is this box here. These boxes here are quite a bit different. So this layer is typically asynchronous. So things happen when somebody decides to do something. But these layers here, thinking about the autonomous cab company or something else, things they must happen in a certain time frame. So if somebody wants to do some customer wants something, we have to deliver the service in right away. Or if there's a physical system involved, like in the lowest levels here, I mean, let's say this was an autonomous vehicle, for example, we would need a completely different type of software here in the lower levels. In some cases, they have to understand the physics of the system, for example. They might be continuous and discrete state variables. For example, they might be changing. According to some schedule, you have to react quickly. So you can't do the same. What is applicable here is not applicable at the lower levels. So the interesting question here is how to build this stack here, and how far below can we go by using general purpose techniques. Currently we believe that this highest level box, it can be very much general purpose, could be applicable to any industry. The rules like these here, you just have different kinds of rules for different industries for different purposes, but the basic scenario would work almost everywhere. So the lower levels I might not be doing, but might be interesting to look at the bottom lower levels in that architecture as well. So I'm not sure whether I have half an hour, 45 minutes. I'm already at 40 something minutes. Conclusion. There's lots and lots of different kinds of AI. I think the AGI type of AI is the most visible. If you read an article on a newspaper, it's always about natural language, speech, or vision, or something like that. Industrial applications are currently not really that visible, but I think they are going to be at least as important as the ones that are closely related to human abilities and skills and communication with humans. I think that obstacles for AI actually revolutionizing everything very quickly are related to the integration of AI in existing systems, existing software systems and otherwise. So you just can't go to the IT guys at University of Helsinki or Aalto University and say, okay, now I have this AI thing, can you integrate it for me? It can't be easily integrated in existing systems unless it's really like a plugin. Something that goes, some input goes through some box and then goes to the software system. If it's something that goes deeper and impacts the mode of operation of an organization more deeply, it's not going to be easy to integrate those typically. What we want to do is automate software production so that AI and other kinds of things are much easier to do, and to rely embedding these automated planning, decision making, and whatever things much easier than what is currently possible. I think it would be very healthy to view AI as an extension and improvement of current software technology. It's not a completely separate thing. It's not a realistic expectation that you will somehow replace with some AI thing everything that currently exists. It has to be something that builds on or improves existing things people do with software. So that's I think the realistic story in how is AI in a large scale going to revolutionize some industries, for example. Okay, that's it. Questions?
Thank you.